Hello everyone, and welcome to the webinar, CARMA Simulation Update. My name is Zach Pleasant, and I'll be helping with facilitating today's webinar. This webinar is sponsored by Federal Highway Administration in cooperation with the National Operations Center of Excellence, NOCO. As a quick reminder, if you don't know already, at NOCO, we offer a variety of resources to support the transportation systems management and operations community. On the upper right-hand side of your screen, you can see a box called Useful Links. You can browse through those links for TSMO resources and news. Previous webinar recordings and case studies related to this topic can be accessed from there. Now I'll cover a few logistics for today's webinar. We are recording this webinar, and the recording, along with the presentation slides, will be available through the on-demand learning section of our website. All the attendees' phones are in a listen-only mode by default, but we'd like you to stay engaged by using the question or discussion pod for comments and questions. We have a question and answer session at the end of the webinar, so if you have any questions, we encourage you to enter them in the question pod as soon as they come to your mind. The questions will be read out loud one at a time by the moderator, and our presenters will answer each question. So that is all I have. And with that, I'll hand it over to our moderator, Bradley Wong, to start us off.
Hello, everyone. My name is Bradley Wong. I'm a communications specialist with Leidos, an FHWA contractor, and I'll be moderating this webinar today. Okay, I see that you've already pulled up the slides, so that's great. As we begin, please introduce yourselves in the chat pod. And as Zach mentioned before, if you have any questions throughout the presentation, feel free to write it in there and we will address them all at the end. And again, I would also like to point out on the sidebar those various links that are related to CARMA. Okay, so welcome everyone to this installment of the CARMA webinar series. Today we will be covering CARMA simulation updates. I'd like to introduce our speakers. We have Jitong Wong. He is the project manager and co-principal investigator and is a senior transportation engineer with over 14 years of research experience. His main focus is on roadside unit and roadside equipment testing and standard development, connected and automated vehicle systems, and transportation modeling and simulation. Dr. Wong is leading and participating in several CAV research projects at the Federal Highway Administration's Saxton Transportation Operations Laboratory, Turner Fairbank Highway Research Center. We also have Kyle Rush. Kyle is also a co-principal investigator on this project and a software engineer who has been working for Leidos at the Saxton Transportation Operations Laboratory on Cooperative Driving Automation projects for over 6 years. He has been involved in the development of 3 generations of CARMA software, Glidepath Eco-Approach-and-Departure, and Cooperative Adaptive Cruise Control applications. Kyle also now helps to operate the CARMA Support Services help desk, providing information and technical support to individuals and organizations interested in applying CARMA in their own research. I would also like to mention Peter Wong. He's not presenting today, but he is the government task manager for this project. He's a highway research engineer with numerous areas of expertise, such as artificial intelligence applications in ITS, dynamic traffic demand estimation, environmental impact of connected vehicles, and hardware-in-the-loop simulation for connected vehicle studies. All right, so the first thing we have here is a disclaimer. This presentation was created and is being presented by an FHWA contractor. So the views and opinions expressed in this presentation are the presenters and do not necessarily reflect those of the FHWA or the U.S. Department of Transportation. So to cover the agenda for today, we will go over the general background of CARMA simulation, the Cooperative Driving Automation simulation environment, the CARMA Everything in the Loop or XIL project, and we will have a questions and answers portion at the end. So before we go into the presentation, I would like to ask a couple basic poll questions, which if you've previously attended these webinars, you might recognize. The first one is, what is your affiliation? I see we have a ton of academia. That's great. A little bit of federal government, some private agencies. Great, so I think that covers everyone. So we have mostly academia, very interesting to see. All right, so let's continue on to the second poll question, or should we? Okay, so now it's closed. My mistake. So the second poll question is, what is your level of exposure to CARMA or Cooperative Driving Automation prior to this webinar? Looks like most people are somewhat familiar. Okay, so just a few that are not familiar at all. Hopefully we can answer any questions that you all have later on today. All right, so now that I've completed the introduction, I'm going to pass it off to Jitong to continue the presentation. Jitong, are you there?
Oh, hello, Brandon. Lee, thanks for the introduction. Can you hear me?
Yep, okay, we can hear you now.
Okay, great. Good afternoon or good morning, everyone. We are glad to introduce our CARMA simulation updates to you. First, I would like to talk about the background of our research. As we know, CDA technology is one of the most promising technology which are believed to be able to solve or mitigate many existing transportation issues such as congestion, safety, emission, and the fuel consumption. To better utilize resources for deploying and developing CDA technology, agencies need to find a low-cost approach to assess the benefits of different CDA application to make intelligent investment and policy decisions because they want to select the best application that can solve the target issues of a transportation system. Traffic simulation and modeling tool is a popular and a powerful approach for federal, state, and the local transportation agencies to evaluate new technology and the strategy before implement them in the field. However, current analysis modeling and the simulation tools were developed based on traditional transportation theories. These tools were calibrated and validated by using non-CDA data. These two gaps make existing AMS tools are not well suited for evaluating connect and ultimate vehicle impact on mixed traffic. So this tool must be improved to enable evaluation of CAV use case in the real-world sightings. In order to address this challenge and better evaluate the new possibility enabled by the CDA technology, a few CDA simulation projects were sponsored by FHWA As the first step, we would like to develop a CDA simulation framework to illustrate critical components of the desired CDA simulation environment. So to identify desired CDA simulation environment, the project team did comprehensive literature reviews and also collected suggestions from CDA technology users and experts. According to the results, multi-simulation focused evolutionary framework for progressing CDA simulation capability is presented as shown in the right side of the figure. This figure shows the desired CDA simulation environment has 5 major simulators: vehicle driving simulator, traffic simulator, traffic management center simulator, pedestrian simulator, and human driving simulator. Different simulators handle different CDA simulation needs. These simulators are synchronized and organized by a central simulation manager. This core simulation functionality is then further enhanced and leveraged by a class of enabling technologies such as augmented reality and virtual reality, cybersecurity, artificial intelligence, and machine learning. Those are not the only potential enabled technologies. Many advancing technology may open new doors for future research, but this area seems most closely related to the current research at this time. So in next few slides, I will introduce this simulator and the enabling technology one by one. So before the CDA technology appears, transportation engineers focus on optimizing infrastructure operation to improve the efficiency of transportation system. Usually we provide more real-time information to drivers, such as dynamic speed limit and variable message size to help them make a better decision to drive their vehicle to reduce congestions and improve the safety. But there are very limited strategies need to control vehicle. By implementing CDA technology in transportation industry, it brings opportunities to let us control both vehicles and the infrastructures to further improve performance of existing transportation system. On the other hand, we also need to have a vehicle driving simulator to make sure the proposed CDA application and algorithm are feasible to be implemented in the physical vehicles, and also make sure CDA-equipped vehicle behaves as we expect. Vehicle driving simulator is not new in the industry. It is widely used by OEM to validate vehicle behavior and vehicle-based application. Currently, it's also used by CDA application developers to create virtual driving environment. Vehicle driving simulator could be used as software in the loop, hardware in loop, and model in the loop, or a mixed approach to meet different purpose. And it can directly integration with CDA vehicle control software, such as the CARMA platform. So traffic simulator is very similar for us. It is also a critical component of desired CDA simulation environment. The traffic simulator can provide microscopic views of behaviors in the traffic system, and it can simulate the effects of the CDA system under test on that network. It is widely used by state and the federal Department of Transportation for evaluating road designs, new traffic application, and traffic management strategy, such as a vehicle driving simulator. Traffic simulator could be implemented by different approach, such as software and loop, hardware and loop, and model in the loop, depend on the research needs and testing scenarios. Traffic Management Center responsible responding to incidents and events that may impact traffic system operation. Because of the vehicle-to-everything communication feature, CDA technology provide an increased opportunity for interaction between CDA-equipped vehicles and the TMC. It becomes useful and necessary to study how this interaction occurs and what kinds of impact it may have on the transportation system. It will help us to develop next generation of traffic management control strategy. So the preliminary model for this kind of interaction is CARMA Cloud, a system which provides real-time data feed into CARMA-equipped vehicles, alerting them to lane closure, weather events, and other events. So TMC simulator could help us for testing new CDA applications involving TMC interactions, such as testing new transportation system and operation use case, and evaluate effectiveness of different TMC strategy or algorithm. So Pedestrian Simulator is another major simulator in the CDA simulation environment because safety is the most important aspect in transportation system operation and management. It's necessary to evaluate actions and behaviors of pedestrians and other road users with CTA-equipped vehicles. For the most pedestrian or bicycle-related CDA application, safety is a major concern for testing this application. So with the pedestrian simulators, the CDA simulation environment could provide a safe environment for testing and the evaluation of vehicle-to-pedestrian system without any risk to participants' safety, because it can actually eliminate the direct interaction between physical human being and physical vehicles. For example, by using the hardware and loop simulation for V2P testing, a pedestrian can work in an isolated room for testing. The actions of the pedestrian will be translated into a simulated pedestrian that's working at an actual intersection to let a physical CDA-equipped vehicle interact with the simulated pedestrian. On the other hand, the human subject will wear VR glasses, which can let him or her see a physical CDA-equipped vehicle in the simulated environment. By using this approach, the physical pedestrian can virtually interact with the physical CDA equipped vehicle without safety concerns. In addition, data generated by pedestrian simulator in the CDA simulation environment, especially hardware and loop simulation, can used for mitigating assumption and improve the accuracy of simulation results. So human driving simulator is widely used for human factor-related study in the transportation field. Integration of the CDA simulation environment with human driving simulator could beneficial researchers in the CDA field. It can increase accuracy of human driver behaviors for CDA research efforts. It also increases the accuracy of CDA applications behavior for human factor research. The same as a pedestrian simulator, if human driving simulator is used with hardware loop simulation functionality in the CDA simulation environment, it could enable safe, accurate study of how human drivers interact with real CDA-equipped vehicles, since human drivers and human driven vehicles only virtually interact with the physical CDA vehicles. So as we mentioned before, simulation manager is the core of the CDA simulation environment, since it coordinates and synchronizes different simulator, especially for data exchange and the time synchronization. The simulation manager becomes more sophistication over time as more simulators are added to the system. Simulation manager also provides a uniform interface to let the user integration with CDA simulation environment by select their desired simulator. So we also want to bring a class of enabling technologies to further help us to conduct CDA-related researchers. So the first technology we want to bring in is augmented reality and virtual reality. These two technologies are very helpful in CDA research. It enables exciting new opportunity and also mitigate or eliminate any safety concerns, especially with hardware loop simulation. Example I mentioned for the pedestrian simulator. In addition, AR and VR also can act as a virtual link between the virtual simulated environment and the physical environment. So it can virtualize interaction of virtual vehicle with physical CDA vehicles and physical human subjects. And it also virtually demonstrates the virtual simulation environment. And it also can help us to do the data visualization for both physical vehicle and the simulation environment. More importantly, it also significantly improves the demonstration capability at a test site. So as we know, connectivity feature of CDA technology provides significant benefits. It also requires us to conduct more cybersecurity and communication related research compared to non-CDA based transportation system. So bring cybersecurity into CDA simulation environment will enable us to conduct attached surface study for vehicle, network, and the infrastructure in order to develop a robust transportation system. It also enables communication between simulators for evaluating different network configuration and congestion levels. For example, we can evaluate whether the channel congestion has a significant impact on mobility or safety application in an urban area. More importantly, it provides us high realistic model of the failure modes in safe test case. For example, it's a safe and low-cost approach to test whether communication interruption may cause collision for a plan tuning application. It also could help us to evaluate the impacts of different communication technology on CDA system, such as the DSRC and the V2X. So artificial intelligence and machine learning are hot topic in engineering and the data-related industry, since they expect to bring evolutionary impacts on this industry. As we know, AI and machine learning have high requirements for the data quality and the amount of the data. Well, CDA technology actually generates huge high resolution and accurate traffic data sets. Also, the CDA technology are still in the early deployment stage. As we can see from this figure on the right side, high resolution and accurate traffic data could be obtained from infrastructure side, vehicle side, TMC, and other source. So this actually brings many opportunities for implementing AI and machine learning into transportation industry. It's necessary for integrating AI and machine learning into the CDA simulation environment. So this slide just shows a list of data sets we can obtain from different sources of CDA-based transportation system. We can use AI and machine learning to help us to process huge historic and real-time data sets in order to predict problems, analysis solution, and also support agency decision-making. Since CDA technology enable more data sets than the traditional transportation systems, it also enable us to establish a new standardized data exchange format if necessary. So right now, the physical CDA-equipped vehicles are still very expensive. Currently, only a few agencies can afford a limited number of CDA vehicles, usually less than 5 vehicles for an agency to develop and testing CDA technology. This limited researchers to test some scenarios for CDA application. For example, if we want to evaluate how multiple plan tools can interact with each other. But this limitation may be overcome by cloud computing technology. Cloud computing technology can support hardware loops simulation with high-speed internet backhaul and high-performance cloud computing cluster, which enable to implement a virtual testbed in the trust sense and also to coordinate testing events between different test sites. This technology, like feasibility, depends on several major factors, such as reliable internet access with sufficient bandwidth and the sufficient maturity in CDA simulation technology, and also latency between different software and hardware. So with sufficient maturity in CDA hardware in loop simulation technology, it may be feasible to consider the development of a cloud-based CDA hardware loop system to enable geographically distributed test events unified by a central simulation server. I believe this is the last slide of my presentation. Yes. So Brandley, I will turn over presentation to you.
Thanks, Tom. So before we jump into the next section, I would like to pose another couple poll questions. The first one is, which of these frameworks are most relevant to your research? A pretty mixed bag. Okay. I see a lot of traffic simulator and a vehicle simulator. All right, cool. And one more poll question. Which of these enabling technologies are most relevant to your research? Okay, a lot of AI and machine learning, cool. Okay, good to know. So with that, I'm going to pass it off to Kyle, and he will present the next section.
Thank you. Hello, everyone. Thanks, Tom, for presenting that overview of the simulation framework. Today, I'd like to talk to you all a little bit more about the CARMA XIL project and how the work we'll be building under that project fits in with that overall picture. So I'll kind of give a high-level overview of what the XIL project is, what its goals are, and then some more information about what we ultimately hope to produce with this product and how it fits into that larger picture. So the goals of the XIL project are to establish CARMA XIL capabilities that do not exist at the moment, to support the development of cooperative driving automation applications and their evaluation within a simulated environment. We hope to begin to build the XIL everything in the loop capabilities with open source software to support the development of tools for the community to understand the broader impact of CDA on the transportation system as a whole as well. So it's kind of a two-pronged interest, one side more focused on the development and testing of CDA applications, and also the ability to use this XIL system to kind of prove out the benefits or whatever effect a CDA system in question might have on the broader transportation network as part of kind of evaluating it for potential deployment in the field or evaluating it for future study. So this is based on the CDA simulation framework that Shatong just presented on. We are developing a subset of the CDA simulation framework to kind of kick off the development, the longer-term development process of this whole framework and environment. The primary focus for everything in the loop is in enabling software in the loop simulation utilizing a vehicle dynamic simulator and a traffic simulator to be able to provide tight integration with cooperative driving applications, as well as to provide the kind of data set and feedback and realistic interactions with infrastructure and traffic signal controls that would be provided by a more traditional traffic micro-simulation kind of software. So by integrating both of these components into an everything-in-the-loop co-simulation environment, our goal is to enable both of those project goals simultaneously with the same software system. So kind of one of the first fundamental steps of building out this XIL project is to integrate the vehicle dynamics simulation and the traffic simulator with the CARMA ecosystem. So the CARMA platform will be the primary cooperative driving automation system under study for the XIL kind of platform. It's the platform we're hoping to use to be able to integrate applications into the simulation environment so we can begin to see their effects either from an individual vehicle level in terms of the controls behaviors of that vehicle or kind of at the broader network level as we are able to evaluate things like how it impacts throughput or other traffic metrics. So we're developing this co-simulation platform to support that goal utilizing CARLA, Cars Learning to Act Simulator, as well as the simulation of urban mobility or SUMO simulation software for their vehicle dynamics and traffic network simulation respectively. So CARLA will be the primary integration point for the CARMA platform, being the vehicle driving simulator suited best towards integrating cooperative driving applications or autonomous driving systems for our particular use case. And that will be handling the sensory aspects of the vehicles, the controls aspects of the vehicles, and so on. And then we will be synchronizing that data into the SUMO environment for the purpose of integration with SUMO's infrastructure components, as well as to get a broader picture for how the CARMA vehicles in a system might impact the broader traffic metrics. We plan to support multiple CARMA platform-equipped vehicles within the simulation environment. So we are working on ensuring that the CARMA-equipped vehicles can be kind of multiplexed through a CARLA instance to support a dynamic operation where we might have fleets of CARMA vehicles or to test different penetration rates of cooperative driving automation technologies into a traffic stream to enable different kinds of studies on different kinds of applications as might be required. Another important component of this whole XIL system is the communications aspect, which is critical to cooperative driving automation. So we are planning to integrate NS3 as the communication simulator into this co-simulation platform such that the CARMA vehicles within the simulation can communicate in a realistically simulated way to model any of the packet loss or latency that might occur within a real kind of network. We plan to use both the existing DSRC wave integration into NS3, as well as we are exploring options for cellular vehicle-to-everything, CV2X capabilities, and how we can integrate that with NS3. And we also plan to explore other potential communication media simulations that might be relevant within the NS3 environment for our particular application. So things like 4G cellular for cloud-based communications to the CARMA platform, for example, are also under consideration. So these components are all going to be linked together through a basic version of that simulation manager that Shashank spoke about. As mentioned, the intent of this simulation manager component is to synchronize the various simulators and ensure that everything's moving in lockstep and that all of the components are playing nice together. And the concept here is that this component will evolve as the build out of future simulation integrations and different components continues. So it's kind of a living component that as the system gets more complex, it evolves with it. The step beyond that, once we have the CARMA platform integrated for the study of its internal cooperative driving automation applications, would be to integrate the CARMA Streets platform into this entire kind of framework. So this is our second step into building out the CDA simulation framework, would be to bring in the CARMA Streets software integrated with Sumo to act as kind of an edge compute device capable of running algorithms for traffic signal priority or other sorts of shared perception kind of applications integrated with Sumo, communicating via the communication simulator with the CARMA platform vehicles to enable the implementation and evaluation and study of those algorithms and how they impact the traffic stream and how they impact the CARMA vehicles and how they perform in and of themselves. So this integration will be done at the Sumo level, also plugged into NS3. It would be communicating with Sumo's internal traffic signal controller logic and would provide kind of an entry point for application development on the infrastructure side of this simulation. And once again, this would come with an increased sophistication of the simulation manager itself to support these new kind of applications or use cases within the simulated environment. Once the XIL simulation platform is finished developing and testing, we plan to release this tool to the public for support of development, testing, deployment of CDA algorithms and applications so that the CDA algorithms and applications themselves can be evaluated by others and run in different scenarios, different test cases to kind of continue and carry on some of this research. We also plan to make it available for helping users to adapt and use the CARMA platform to support their own CDA research, whether this is at the prototype phase before building applications to deploy on physical vehicles, or whether this enables those who might not have access to physical CARMA platform-equipped vehicles to enable them to conduct their own cooperative driving automation research without having to go through the expense of acquiring a vehicle. The project team also plans to provide technical support to users under the CARMA Support Services program. The CARMA Support Services program is a help desk run by the Saxton lab that provides technical support services, documentation, troubleshooting to users seeking to use any of the CARMA program software or having questions in general about cooperative driving automation. So this help desk will, at this point, provide support for the XIL co-simulation platform once that's made publicly available. To reach out to that help desk for any sort of assistance with CARMA software, architecture, CDA-related questions, simulation-related questions for CDA, please email CARMA Support Services or carmasupport@dot.gov. That support email line is monitored Monday through Friday, 8 p.m. to 5 p.m. EST and Daylight Savings Time, with the exception of holidays. And we do try to respond to any questions or concerns that we receive within a timely fashion. So please feel free to reach out to that email with any questions or comments you guys might have. And we will certainly do our best to provide you any sort of information that you might be looking for. And I believe that is the last slide. So I will pass it back to the group for questions and answers.
Thanks, Kyle. So this is the time to ask any questions if you have any, and just put them in the chat. I see a few in here already, so I'm going to start with those. We have one from Mohammed. He said, it would be good to mention what are the inputs and outputs of the various simulators.
So this is Zhitong. Actually, this is a good question. For the portion of the simulation I did, I just present a comprehensive framework, which is a long-term development goal for us. Currently, we just start to work on the Everything in Loop project. That may be the first step. We will build the we start to build the CDA simulation environment. So we are working on working on the framework and the architecture design document for this project. So we will provide such information in that document. We would like to present or share such information with industry when the document will be ready. As we know, the CDA technology is developing rapidly, so we think maybe it's good to just develop the design and architecture document when we decided to bring each simulator into the simulation environment. So, Kyle, do you have any comments to add?
No, I think that's a generally good response. As we build out each of these components of the CDA simulation framework and select concrete tools, simulation platforms to use, we certainly plan to continue to update the documentation and go in more technical detail with our publications as far as what specific data we'll be extracting from each of the co-simulation elements involved. But at the moment, since it is more of a longer-term vision, we haven't yet committed to any tools beyond what we're planning to use for the XIL project.
Okay, so the next question from Dennis is, could you shed more light on the fidelity of the models in the vehicle powertrain simulator for what regards energy consumption analysis?
So this kind of aligns with also the previous question to a bit of an extent. At the moment, the concrete selections we've made for the co-simulations like CARLA for the XIL project, there is not much present in the way of vehicle powertrain modeling in the sense that it's modeling the transmission or the engine. There's a physics simulation applied to the vehicles. But it doesn't have the sophistication of dedicated vehicle powertrain simulation, for example. So part of the layered approach of the layered and modular approach of the co-simulation framework is to enable the integration of maybe a dedicated powertrain model within the overall system. But we don't have a particular model in use at the moment.
All right, and the next question is also from Dennis. Are there any specific projected timelines for rolling out these XIL CARMA co-simulation functionalities?
The XIL project? No, go ahead, Zhitong.
Go ahead, Kyle.
Yeah, sure. So the schedule for the XIL project is the project itself is under development now. We, I believe, plan to do our initial rollout of some of the releases of this software in the fall. Zhitong, please feel free to correct me if I'm wrong. But that would be around when we complete the initial integration of the CARMA platform itself. And that would include the co-simulation between Sumo, Tismo, or Sumo, NS3, and CARLA.
Yeah, Kyle, you are right. And for the second version, which will develop an interface between this co-simulation tool with CARMA Street. The release date would be the first quarter of next year.
Okay. The next question is from Guoyuan Wu. Are there any challenges in synchronization for co-simulation platform development? If so, how did CARMA team handle these issues?
So, Kyle, do you want to answer this question?
Sure, yeah, I can take this one. Co-simulation synchronization is certainly a challenge on our radar. One of the aspects we've looked at is using dedicated co-simulation frameworks that exist out there today to see how they approach simulation synchronization and how they manage the time synchronization aspect of all this, because we definitely do need to keep them in sync to ensure smooth operations and that the simulations are accurate between time steps. So one of the solutions we have on this regard is we are kind of basing some of the XIL work off of an existing open source project called Mosaic, which provides some level of integration between Sumo and Carla, as well as the time management for that interface. So we are extending and modifying that open source project for integration with CARMA and CARMA Platform and CARMA Streets, and extending some of the capabilities of the simulations within that co-simulation environment to align itself with our specific XIL use case for the CARMA Platform.
All right, and the next question is from Omkar. Is the co-simulation tool different from what we already have? If not, will this be available in GitHub, and what is the system configuration needed to run the co-simulation tool?
Oh, I may answer this question first.
Sure, Tom.
Yes. I'm not sure whether the co-simulation tool we already have indicates the co-simulation interface between Carla and the Sumo developed by the Carla development team. If it is, yes, our co-simulation tool is different with that one. As Kyle mentioned, we were redeveloped the co-simulation tool by using the Mosaic framework. So we were develop our own interface between the Carla and the Sumo. We also want to improve the existing interface between Mosaic and the Sumo, and also between Mosaic and an FHWA. We need to add the CV2X simulation capability to an FHWA as well. The major reason we select Mosaic is we would like to have a standardized and dedicated co-simulation framework, which can help future users to adapt our co-simulation tool, and also can help future users to easily build an interface between our co-simulation tool to any module you develop for your project, so you can have the Intel co-simulation package to meet your CDA simulation needs. So, Cal, do you have anything to add?
I think that mostly covers it. But yes, the core takeaway, I would say, is that this is an evolution of the existing CARMA simulation package on GitHub. This will be available in GitHub, and once it's available, there will be a CARMA config setup as well to run this co-simulation environment in much the same way as there is for the current CARMA simulation package, as well as the rest of the kind of CARMA project environment.
All right, and the next question is, are there dedicated HIL simulators this co-simulation framework is being designed for? If so, could you shed some light on this?
This is Zhitong. So for the current project we have, everything in the loop phase 1 project, we only focus on software in the loop. Yeah, in the future, we may consider to expand our software in the loop framework to include hardware in the loop to bring like physical CDA vehicle and other critical CDA hardware into the simulation. Currently, we use Mosaic as our simulation framework to integrate different simulator. I think we will still use Mosaic as our major simulation framework for hardware and loop simulation in the future, but we may do a re-evaluation when we will do any hardware and loop simulation in the future.
All right. If there are any more questions, please type it now. I saw. Okay, so maybe that's it. All right. Well, it seems like there's no more questions. So thank you, everyone. I do want to point out those web links again. So if you want to shoot us an email, that's also there under CARMA Collaborative email address and CARMA Support Services email address. We also have the FHWA sites for CARMA and specifically CARMA Simulation, as well as the GitHub for CARMA right there. I'm going to pass it off to Zach, and he will close out this webinar.
All right. Thank you, everyone, for attending today's webinar. I also want to thank our panelists and moderator. We had some good information today. Like I mentioned in the beginning, a recorded version of this webinar, along with the presentation slides, will be available on the NOCO website. On behalf of the National Operations Center of Excellence and our presenters, thank you for joining us today, and have a great rest of your day.